Okay. So, what we have done so far, we have tried to discuss about Fourier series, right, and especially the origin of Fourier series, means how Fourier series has come into picture. So, I will just quickly recapitulate what we have achieved so far. So, given a vector analogy, we have said that any vector, if you know the dimension or whatever vector space you have, if you know the dimension and if you know means as many orthogonal vector can exist in that particular dimension. Suppose you have a 2-dimensional thing and you have 2 orthogonal vector. So, what we have said that as long as you know these 2 orthogonal vector, you can represent any vector in that space, in that 2-dimensional space with respect to these 2 vectors, especially the linear combination of these 2 vectors. And these 2 orthogonal vector are actually termed as the basis vector, right. We have taken that same analogy into signal. So, our target there was of course, we have started targeting a periodic signal. So, what we have said, given any periodic signal that can have any nature, can we really find out some known signal, a linear combination of them can give me back that same periodic signal. So, any signal possible in this world which are periodic with some period, let us say t0. Okay. So, can we get set of basis signal, okay, or set of signals which are already known, like this orthogonal signal. So, already known, and can we represent and can we guarantee that any signal in that particular signal space can be represented as linear combination of all those known signals. So, what in that aspect we have defined few things, I am not going into the details of those things. So, we have defined what do we mean by orthogonality condition in signal space. Okay. So, if 2 signals x1 t and x2 t, if these 2 signals are there, both are periodic signal with a period t0, let us say, and then how do we actually prove that these 2 signals, or how do we test that these 2 signals are orthogonal. So, this is something we have already evaluated. Okay. We have evaluated 2 conditions. One is if both signals are real, then we have evaluated one condition, and then we have said if both signals are complex, then also we have evaluated one condition. So, the ultimate condition which we have also proven is that x1 t x2 t over that period, let us say minus t0 by 2 to plus t0 by 2, this must be 0 if both the signals are real, and at the same time if signals are complex, then you have to take x1 t and a complex conjugate of the other signal x2 t, and you have to do the same integration over that same period, and this must give me 0 if x1 t and x2 t are orthogonal to each other. So, what we have to now do, we have after that we have said we should have a quest of this known signal, all the orthogonal signal in that signal space we must be able to find out, as many are there. Okay. So, in that process we have defined 2 things. One is trigonometric Fourier series, that means all the signals must be decomposed into means series of sinusoidal or cosinusoidal. So, that is one. Another one was exponential Fourier series, again all the signals must be decomposed as linear combination of exponential functions, right. Remember, if the signal targeted signal has a period t0, all those exponential signal, or it is a complex exponential signal, all the exponential signal also must have period of t0. So, in that process trigonometric one we have already done. Exponential we have said that e to the power j 2 pi f0 n t. Okay. So, that is the signal we are targeting, and we are calling this as all those xit or xnt. Okay. So, basically it is a, as you can see, it is exponential, and you can put Euler's theorem and then you can get 1 cos plus j sine, and then the period will definitely be 1 by f0, right. So, f0 is the frequency. So, for any value of n, there will be a period which is defined by 1 by f0, which is called as t0. Okay. So, this period will always be there. So, all these signals are periodic signal effectively with period thus, and remember these are all complex signal. So, we need to orthogonality condition, we need to actually prove it from that complex perspective or complex signal perspective, that is the first thing. Okay. And with this we have actually shown that these signals are orthogonal with respect to different values of n, right. So, we take different values of n, you can immediately show that it is orthogonal. So, whenever suppose we take two values m and n, and then you put that orthogonality condition that we have just discussed, you put that, you will be seeing that if m is not equal to n, it will be always 0. Okay. So, these signals are all for different values of n, up n starting from 0 to infinity and minus infinity. So, for all these values of n, they are all orthogonal to each other. There is another aspect of it in vector also, we have told that eventually what we were targeting, any vector we are targeting to represent by another known vector, right. And in that process we are targeting the error of this representation. So, we have said that this is that error. So, if suppose this is my g and this is my x, and if g has to be represented by x, we are giving some linear coefficient Cx, and then this was the error, and our target was to minimize the error. Same thing we have also done with respect to the signals, and then we have evaluated all the values of Cn that is required for different signals, right. So, that is something we have already evaluated. So, it is the error that we are targeting to minimize, right. And eventually we have also said that in the vector space, suppose in this one we are just trying to represent g, which is a two dimensional vector, by one vector. So, that is why there will be always a error. We can minimize that, but there will always be a error. But if we have another vector which is orthogonal to this x, let us say y, we can always completely represent g with respect to linear combination of x and y. We know that already. In a two dimensional space, if we have two orthogonal vector, we can always represent that. So, that means if you have a completeness of the basis definition, whichever space you are defining, if all the orthogonal vectors in that or all the orthogonal basis vector are already defined, then you can always have a linear combination and you can make your error 0. Same thing happens to the signal. If I have a complete definition of basis set, then I can always represent a signal with respect to linear combination of them, and we also know how do we calculate the individual coefficients. So, this is just a complete recapitulation of what we have achieved so far. Okay. So, with that aspect we have talked about completeness, and we are just saying without proof that for all values of m, let us say all values of n, n going from minus infinity touching 0 to plus infinity, okay, every integer value it takes. If we take all this, then this makes a complete basis set, this particular e to the power j 2 pi. So, we are just stating it without proof, and then we can say any particular signal gt which has a period t0, it might have any shape, that can be always represented as a linear combination. So, with coefficient Cn e to the power j 2 pi f0 n t, n going from minus infinity to plus infinity, right. So, this is something we can always talk about, where the Cn's are evaluated just by that error minimization process, which was evaluated as 1 by t0 integration whatever that gt is there e to the power minus j 2 pi f0 n t dt, right, and it should be integrated over that period, let us say minus t0 by 2 to plus t0. So, that is the Fourier series, and corresponding coefficient we already know about, right. This is something we will already know. Now, let us try to see if this is the representation. In this representation, what do we get? We have already seen that in trigonometric representation we actually get different sinusoidal, right. So, at different frequency. This is also exponential representation. So, it must be a sinusoidal, it is a complex sinusoidal. So, let us try to see what do we get. So, first let us try to evaluate what do we mean by this. Okay. So, C, that coefficient evaluated at minus n, and I am trying to take the complex conjugate of that. So, let us first put what is C minus n, that should be whatever my signal is, let us say my GT e to the power minus j 2 pi f0. Now, here that coefficient should come, at that coefficient it has to be evaluated. So, that particular coefficient minus n into t dt, it must be integrated from minus t0 by 2 to plus t0 by 2, and there is a complex conjugate of this. So, the whole thing has to be conjugated, right. So, it should be minus n, I have forgotten that, right, because we are evaluating the coefficient at minus n. So, correspondingly the coefficient should be minus n, and if this is minus n, what happens? This minus minus, it becomes plus, right, and then we are taking complex conjugate. So, integration has nothing to do with it. So, it will come inside the integration. GT is a real signal, we have already talked about that we are evaluating the Fourier series of a real periodic signal GT. Okay. So, GT is real, so complex conjugate of that will be just GT, and the complex conjugate of this one. So, what that will be? It is already minus minus plus, and you take the conjugate of that, that should be again minus. So, I should eventually get 1 by T0 minus T0 by 2 to plus T0 by 2 GT e to the power, again I get back minus. So, there are two negation, minus minus becomes plus, and then you take complex conjugate, so it again becomes minus. We can identify this, this is exactly Cn, right. So, what a very nice thing we have observed now. What happens whenever we evaluate these coefficients, C minus n is actually a complex conjugate of Cn. Okay. So, always C minus n, for any value of n, they are always a complex conjugate of Cn. What does that mean? Let us say my Cn, these are complex number. So, it must have a amplitude and a phase. So, I can represent that as Cn, and then there should be a phase which is, let us say, e to the power minus j theta n. Okay. I can represent it this way, because Cn is a complex number. So, it must have a amplitude and must have a phase, right. So, that is all we are doing, we are just putting this representation as amplitude and phase. Okay. So, if this is the case, what must be the complex conjugate of that? So, C minus n must have amplitude remains the same because it is complex conjugate. So, it must be Cn, and this will be just conjugated. So, e to the power minus j theta n, complex conjugate will be plus theta n. So, what is happening, if, because now every coefficient have two parameter, if I can see, it has a amplitude, it has a phase. So, I can have eventually two plots. One is with respect to this n, I can plot the amplitude. So, what happens to the amplitude? If at n positive I get some value, at n negative the amplitude should remain the same, right, because for Cn also it is mod Cn, for C minus n also it is mod Cn, right. So, the amplitude should remain the same. Therefore, what do we get? For different values of n, the values might be different, but whatever it is at minus n, the value should be same, right. So, we get a even symmetry in terms of the plot, right. Whatever we get at positive half, we get same thing at the negative half. Okay. So, that is why it is called even symmetry. And for phase, just the opposite, whatever we get at positive, we will be getting just the negative of that, right, because you can see, if it is minus theta n, it should be plus theta n, if it is plus theta n, it should be minus theta n. So, the angle should be same, but it is just negated, right. So, we get odd symmetry for the phase plot. So, basically what we are getting now, we have a signal GT, right, it is continuous in time. What we can see now, that GT, as long as it is periodic, it can be decomposed into multiple complex sinusoidal. This is something we can immediately observe. And those sinusoidal, for different values of n, it is actually representing different frequency component. If n equal to 1, it is f0, n equal to 2, it is 2f0. If n equal to minus 1, it is minus f0, n equal to minus 2, it is minus 2f0. So, it is actually representing different frequency component, or we should say different sinusoidal with different frequency value. Okay. So, all we are doing is now, because we have got, if you see this, we have got two equivalent representation of the same signal. GT in time I can plot. I can also plot GT, or I can represent GT as a summation, infinite sum of course, as a summation of sinusoidal at different, because this is just a complex sinusoidal which is known. Okay. So, it is just that complex sinusoidal, all we need to know is at every frequency component what kind of amplitude it has and what kind of frequency it has. So, the information about this signal is completely carried over here, because this is a known thing. Okay. All these signals are known, they are just representing different complex frequencies, nothing else. We just have to know the corresponding coefficient, because as the coefficient changes, it will represent different signal. That is all we are targeting. Okay. So, therefore, thanks to Fourier, what we get is a separate representation of a signal. Now, we do not see the signal in time domain. Whenever we have a signal, we know that it has an equivalent Fourier series representation as long as it is periodic, and immediately we can plot, and effectively we have to give two plots, one for amplitude, one for phase. And we also know that the amplitude plot should be symmetric or even symmetric. So, therefore, positive half whatever it is, it should be mirror imaged at the negative half, and the phase plot should be odd symmetric, that means whatever we get in the positive half, that should be just negative of that in the negative half, right. So, that should be the case. So, we should plot mod Cn and theta n. So, all we have to do is this, and we know that for which point in this independent axis we have to plot, these are just those n value, or more precisely n into f0 values. So, those frequency, those complex frequency component, how much of that component is present in phase as well as in amplitude. So, how much of those components, if I mix them all together, my desired signal will be generated. So, this representation is called the frequency domain representation, because we are actually decomposing our whole signal into different frequency components, that is all. All that we are doing is this only. There are two strikingly different representation when we do it in trigonometric series and when we do it in exponential series, but the function must have unique representation in frequency. So, let us now try to appreciate what exactly is the relationship between these two representations. When we have started representing it in trigonometric series, what we were getting? We were also getting two plots actually, because we had that sinusoidal as well as cosinusoidal. At every frequency we were having both the things, right, barring 0. 0 was only having a DC value, so it does not recognize whether it is cos or sine, because it is not having any frequency component, right, it is DC. So, at that point it was just A0, but rest of the case it was always having a pair an and bn corresponding. An is due to the basis function cos 2 pi f0 n t, and bn is due to sine. Okay. So, these two frequency component were present. If you see that representation, there was nothing called negative frequency, okay, which we are getting over here in the exponential representation. So, exponential representation have the spectrum starting from minus infinity to plus infinity. So, it has some component at the negative frequency as well as positive frequency, whereas when we are representing it in trigonometric, that also has, and this also have two plots, one is amplitude, one is phase. Whereas whenever we are representing in trigonometric form, it was also having two plot corresponding to sinusoidal and cosinusoidal, but it does not contain any negative frequency, right. So this is something we have observed. So we are always getting two plots, and in this two plot, what was coming? It was just those mod Cn at every value of n, mod Cn and theta n. That is what we were getting. Okay. And then we were getting this for the other case, we are getting An and Bn. Now let us try to see if we can correlate these two things. That is the first task, and then we will come back and try to explain what do we mean by this particular thing called negative frequency. Okay. So first let us be concerned about this relationship. So what happens? We have seen that there is a, already we have explored that there is a relationship between C plus n and C minus n. So what we will try to do is, we try to pair up these two things. So we have a representation of Gt as summation Cn e to the power j 2 pi f0 n t, n going from minus infinity to plus infinity. Okay. So let us separate out the C0 term. Okay. So at C0 n is 0, so this becomes e to the power 1, right. So that is all right. And then we start pairing each of those n and minus n, right. So here we will do a pair of C1 and C minus 1, so on. Let us try to do it for Cn e to the power j 2 pi f0 n t plus C minus n e to the power, definitely it will be minus n, so minus j 2 pi f0 n t. Okay. Let us try to see what this term together gives me. See, if I can evaluate all these terms, I am almost coming to a conclusion that it is almost like this C0 is nothing but A0, and this is actually almost like An cos and plus Bn sin. If I can finally represent them in that format, then I can give a relationship between this Cn and An Bn, right. So let us try to see. Now all we know is Cn is a complex conjugate of C minus n. Therefore, I can immediately put a representation. So I can say that suppose Cn is represented as mod Cn e to the power j theta n, then C minus n must be represented as mod Cn e to the power minus j theta n, right. This is something I can always do as long as I know this theta n and mod Cn, and that I should be knowing, because if I know the Cn, I can immediately calculate its modulus and its phase, right. So this is something I can always do. Now let us try to see, if I put this, replace this over here, what do I get? So for the nth term, I can get mod Cn e to the power j theta n e to the power j 2 pi f0 n t plus mod Cn e to the power minus j theta n e to the power minus j 2 pi f0 n t. Okay. So this is the nth term I am getting, which is nothing but mod Cn gets common, and I get e to the power j theta n plus 2 pi f0 n t plus the negative of that, right, e to the power minus j, same thing. Okay. So if I just say it is a e to the power j some theta, or let us say phi, plus e to the power minus j phi, put Euler's theorem, what do you get? 2 into cos of that, cos of inside whatever phi is there. So I can write this easily as 2 into cos theta n plus 2 pi f0 n t, right. What I have eventually got is a single cosinusoidal term, right. I have got a single cosinusoidal term, nothing else. This is something I am getting. Okay. Similarly, for the trigonometric series, for every nth value I will be getting one a n cos 2 pi f 0 n t plus b n cos 2 pi f 0 n t, sorry, sine, right. I will be getting this. Now, this one, what I can do, a n I can write as some r cos phi, and b n I can write as r sin phi. This is something I can always write, right, because immediately I can see, I can calculate r. R should be what? Root over a n square plus b n square, and phi should be, if I just divide these two, tan inverse b n divided by a n. So, as long as I know this relationship, I will be always able to put this representation, put this over here. So, I get r cos phi cos 2 pi f 0 n t plus r sin phi sin 2 pi f 0 n t. Why I am doing this? I just want this representation again, right. Can I see a single cos representation? It is cos A cos B plus sin A sin B. So, that must be cos A minus B, right. So, I can write as cos 2 pi f 0 n t minus phi, fine. So, now I can see I have got two series, one was exponential series, another one was trigonometric series. From both the series I could actually get, I was trying to see the nth term, and I could see that by unifying this cosinusoidal and sinusoidal, and by unifying the Cn and C minus n, I could get similar representation. Only thing is that those coefficients has to be now matched, right, because I will be getting exactly similar term for every n. So, therefore, the coefficient, because it is a unique signal, so it must have unique representation, unique addition of sinusoidal. Okay. So, therefore, coefficient must match. So, therefore, r must be 2 of mod Cn, right, and this phi must be minus of this theta n, right. So, this is what we are getting. Now, phi is tan inverse b n by a n, that must be minus theta n. So, this is one relationship I get, and r is basically root over a n square plus b n square, that must be 2 mod C n. So, basically what is happening, I have got a trigonometric series, I have got a exponential series. Exponential series, whatever amplitude plot I get, I immediately can get a relationship between the corresponding trigonometric series. Okay. So, if these two are equal, the representation should be equal. And what has happened fundamentally, as you can see, that because of this complex conjugacy, finally when I added those two terms C n and corresponding to C minus n, I have actually got a real signal. So, that means my signal was real. People might be thinking that when I do exponential Fourier series, I am representing them in terms of complex signals. So, what is happening to my real signal? Complex signals are now creating real signal, but that is not the case. The Cn's are arranged in such a way that if you take two nth terms, they will, those two complex signal will actually give you back the real signal. Okay. So, eventually it is nothing but both the representation tells you that it is a particular representation where the, for a particular frequency there is an amplitude and there is a phase, nothing else. Both the representation gives you similar value. Okay. So, with this I will end this class. The next class what we will try to do, we will try to evaluate what do we mean by this negative frequency.